you know, like mathematics won't one day wake up and say it doesn't love you anymore. You know what I mean? Math can't do that to you. Math always loves you. Yeah. All right, so we are going to be moving on. All the test 2 material has been covered. Time to move on to test 3 material. I need a good chalk, not these stubby kinds. I'm trying to avoid going to my office, but we'll just have to make do for now. Let's see how much I can use these for. Okay. Also, let me bring this chat up in case people are asking stuff. All right. So let's talk about double integrals. So this is, I forget which section. Last section we went over was 11.8. This is a new chapter, so it's probably 12.1. Probably. Yeah. So here's a theory, real quick. Let f be a function that maps the interval a, b onto the real numbers. Okay. Recall from Calc 1, we can partition the interval a, b into n subintervals. Where this is like a general piece of it. And so if you had some functions right here, we can build an approximation to the area using Riemann sums, right? Where each rectangle has, if this right here is xi minus 1, this is xi, this is, you know, delta x, and the height right here, this height here is your f of x, I star, which is like xi star is right here. So you'd say that one rectangle is length times height. So here's our height times our length, a delta x, right? So all of them gives me the sum from I equals 1 to n of f of x I star delta x. And that implies this is how we define the limit. It's when we have an infinite number of these triangles. I equals 1, I mean. And this is defined to be the integral from a to b of f of x dx. So that delta x turns into a dx. That f of x I star across an infinite sum becomes just your function evaluated at every dx. Review. That was integrals and Riemann sums in Calc 1. So now we're gonna try and find volumes. So let's say we have a 3-dimensional situation. We got some surface here, some surface S. All right. And let's say the surface S is equal to some z of f of x, y. All right. It casts a shadow. Its projection casts a shadow. Right? Well, that's a horrible shadow. This leg needs to come out in front, right here. There we go. Boom, 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 boom. It's supposed to look more rectangular, but that's okay. Doing this in a hurry. That's its projection. We call this projection down in, like, let's say the XY plane, some region R. Okay, so this surface right here, any point P on this surface has some x, y, and some f of x, y, right? Which you could call that z. But then we project it down to this region R, or an arbitrary point here is just some x, y, okay? Then we say, well, what does x and y, where does x range and where does y range? Well, we say that that region R can be defined as the set of all x, y, such that, clearly this is an R2. We don't have to really say it, but we can. Where this is true. X ranges from A to B, and Y ranges from C to D, if you will. Some arbitrary parameters. And let's say we set them equal to. So then R is then defined to be the Cartesian product like so. Then this thing, this S will then be defined as the set of all x, y, z, an element in R3, such that this is true. Okay. And here's the key point that the x and y is in R, this guy. All right. Then we can say, oh, see this R right here? We can create, just like we had rectangles, we can create something similar. In that projection, here's the x, here's the y. Here's some like xi minus 1, here's some xi, here's some yi minus 1, here's some yi. Notice that right here, this shaded region, if we say that the difference between here is a delta x, and the difference between here is a delta y, that region is delta x times delta y. Right? Length times width. Boom. Okay? Then you could get even more fancy and more precise and say, define this centroid of this polygon and say that, okay, this is yi star. Actually, we could call this a j. We can call this a j, call this a j to have them have different indices. And this is some xi star, where you can define xi star as being the average between xi and xi minus 1. Some type of sample point, which would make your answer be more accurate. But you know, the left midpoint, the left sum, the right sum, the midpoint, the Simpsons rule, the trapezoid rule, all of them, when n approaches infinity, all of them approximate the integral, no matter what. So it doesn't matter what we do. I'm just doing this to be kind of consistent with the book's derivation. It doesn't really matter. When n approaches infinity, all of those approximations approach the actual integral value. All right, so then this is the two-dimensional version of what I erased. It was that R. Notice to get the area, we have to get that column. So we have to add the height into the picture. So this is length times width. Then what is the height? It's the function's value. So one column is length times width times height. The function evaluated at that value. This is like some z sub I star. And because there's indices I and j, we can put I and j. Okay, so then you get a volume. X, Y, Z is equal to a volume. That's a volume of one column. So what happens when we add up all the volumes of all the columns? We get a double Riemann sum from I equaling 1 to n, j equaling 1 to m, of some f of xij star yij star delta x delta y. If you want to remember what they have indices, then that's that. So that's the double Riemann sum. So when we take the infinite limit, guess what? We're going to get a double integral. So this implies that the limit as m and n approach infinity of, let's call this whole thing that. I just don't want to rewrite it over and over again. Just the limit as m and n approaches infinity of this thing converts it into the integral from c to d, integral from a to b of f of x, y, dx, dy. Where'd that a to b, c to d come from? Remember, x, r, so this is actually going to be equivalent to the double integral across the region r of f of x, y, dA, where dA is called a cross-sectional area element. Really, dA is a cross-sectional area element. It's really the product of the dx and the dy. And R is our region. Remember, R is defined as being the Cartesian product of these two closed intervals. So these are the same. Now, let's actually use it. Now that we've defined it. So let's let z, a function of f of xy, be 16 minus x squared minus 2y squared. All right. And let's let r equal 0, 2 cross 0, 2 estimate this. Okay. Really, this is the double integral from 0 to 2, 0 to 2 of f of xy dx dy. Okay. And how can we estimate it? We draw a picture. So this is 1, 2, 1, 2. This has area 1. This has area 1. This has area 1. This is area 1, right? 1 times 1 is 1. Okay. So really, it's saying, what is this total area? Okay. Now, this is the two-dimensional version. We can't forget the height. This is the z, and this is the negative z, right? That's the plane, and that's the height. So how high does it go? That is your f of z at each of these points. So this goes up to like f of 2, 2. This goes up to f of 1, 2. This goes up. Whoops. This should say 2, 1. Right? And this should say f of 0, 2. No. It should say 2, 0. X comes first. Dyslexia a little bit. So yeah. So to get this, we can estimate it by saying, what is this dA times what is the height? So each piece is going to be being multiplied times 1. So this integral is the same thing as your 1 times your f of 0, 1, plus your 1 times f of, why am I saying 0, 1? We start out with 1, 1 to get a non-trivial area. Then we go f of 1, then we go to f of 1, 1 is here. Let's go with 1, 2. And then here's 1, 1, 1, 2. Here's 2, 1. And then plus 1 times f of 2, 2. Okay. Really, we're calculating volumes. This is a volume. This is a volume. This is a volume. This is a volume. It's all three of the columns that emanate. And the height is dictated by how much is the function evaluated at those points. So clearly, like 1 times f of 1, 1 is the same thing as f of 1, 1. And that's the same thing as like 16 minus 1 squared minus 2 times 1 squared. This is equal to 16 minus 1 minus 2 is equal to 13, right? So this piece turns into a 13. So if you do this process, you get 13 plus a 7 plus a 10 plus a 4, and they add up to a 34. So that's how you can estimate it. All right. Let's stop estimating, though. Let's do something analytical. What about the integral by the of the region R, 1 minus x squared dA, where our region is now defined to be the set of all x, y, an element in R2, such that x ranges from these values and y ranges from these values. It's helpful to do some algebraic trickery to visualize this shape, this geometrical object in R2. We can set the inside of the function equal to some variable. Your book sets it equal to z, but you could have set it equal to y. It doesn't really matter. Okay. Notice when you square both sides, you get this. Now the variable you set it equal to will change the way your shape looks, but it won't change the integral. It'll just change where your shape is emanating out of. It emanates out of the free variable. This implies we get a z squared plus an x squared is equal to 1. What is this? Yeah, it's a circle, but we can't forget that y is a free variable, because we don't even talk about y. So that means y can be anything. So it would have formed a circle emanating across the y-axis. But now, since y is free, it's going to form a cylinder. But also, we have to note that z is greater than or equal to 0, meaning it's just a semi-cylinder, just the top part of a cylinder. Okay, why is that? Well, because if we retrace ourselves and we go to here, and let's say we took the square root of both sides, this would imply that z is equal to plus or minus this quantity, right? That would have given you a full cylinder, both of them. But we're only taking the plus. We're just getting the top half of the cylinder. The plus was only what we were given. Yeah, it's a technicality, but if you don't adhere to it, you get very wrong answers. Woo! That's why they warn you, don't use stubby chalk. has perils. Like, what just happened? Ooh. Okay. So let's then think about what this shape looks like in R3. Here's a negative y, here's x, negative x, and here's z. So take a look. X ranges from -1 to 1, so here's 1. Here's our -1. Y ranges from -2 to 2. Here's our -2. Here's our +2. And what we get is a half of a cylinder. The top half, the positive half of a cylinder. Where the cylinder is supposed to look like a real good cylinder. At this point, this is at the radius of the cylinder intercepting the z. The radius of the cylinder is 1. Right? This equation tells us that. Then we can calculate what is the volume of the cylinder. Right? But it's half of that. Right? And then, what's the height? It's the distance from here to here, which is 4. What's the radius? Right? So pi. So then we get this. These cancel to give me a 2. That becomes a 1. Just 2 pi. Another estimate. We're able to estimate it because we know what the volume of the cylinder is. So why resort to the heavy machinery of calculating the integral? Okay. We have not yet calculated integrals freestyle yet. We've still resorted to doing estimates, but that's okay. Mathematicians do that. It just goes to show you what these integrals represent. These integrals represent volumes, and you can calculate an integral by finding the volume. There's a midpoint rule. I expect you to just look at that yourself and learn it. Now let's talk about iterated integrals. Okay? We've discussed how this is equal to from C to D, A to B. Where your R so for example, let's calculate what does this equal? Well, the order in which we have the integrals, the dy is here first. So really, we can integrate the first integral. Okay. So then we just write the outer integral. We reproduce what that says. And we find what that inner integral equals initially. This is a partial integral, just like we had partial derivatives. Right now, the integral only perceives the y as a variable. It thinks x squared is a constant. Okay? So to honor that, I can actually write this. Now, all we got to do is calculate the integral of y with respect to y. What is that? Yes, ma'am, you are correct. And we got to evaluate it at y equals 2 and y equals 1. Okay. So then this becomes integral from 0 to 3. I can factor out that 1/2. I get x over 2 over here. And my y 2 squared minus 1 squared. Okay, that's this piece dx. So then this is equal to the integral from 0 to 3 of x over 2 multiplied by something dx. And that something is 4 minus 1, which is 3. Okay. So then, now I got the integral 0 to 3 of 3x over 2 dx. That integral ignores the 3 over 2. It only considers x a variable. So this just becomes the 3 over 2. Integral of x is just x squared over 2. Evaluated at x equals 3 and x equals 0. So this becomes 3 over 2. I can factor out another 2 to get 3 over 4. And so this becomes 3 squared minus 0 squared. And this becomes 3 over 4 times 9. Which becomes 27 over 4.
Should the x divided by 2 be x squared divided by 2?
Yes. X divided by 2 should be x squared divided by 2. That's what's going on here. So, wait a second. Yes, it should say x squared divided by 2. So once we integrate it, we're not integrating this. Thank you very much. Okay, so that should say 3 over 2 integral of x squared, which is going to be x cubed over 3 evaluated from 0 to 3. Aha, it changes these calculations a little bit. So then we get the factoring out the 3, I get a 1/2 times 3 cubed minus 0 cubed. So this becomes 1/2 times the 27. And this becomes a 27 over 2. Okay. Very good. Now let's consider what happens if we switch the order of integration. What does this equal? It's the same integrand, same limits of integration, just different order. We now are going to integrate with respect to x first. So this becomes integral from 1 to 2 of x cubed y all over 3, evaluated from 0 to 3, dy, which is the same thing as integral from 1 to 2. And I can factor out a y over 3. Actually, yeah, y over 3. And so then we're just going to say 3 cubed minus 0 cubed. So this just reduces to a 27. So 27 divided by 3 is 9. So I get this is the integral of 9y dy with limits of integration 1 to 2. And when we integrate, I get 9 y squared over 2 evaluated from 1 to 2. And so I factor out that 9 over 2. And so I get this is 2 squared minus 1 squared. Okay, and so I get this is 9 over 2, 4 minus 1. So this becomes a 3. 3 times 9 is 27 all over 2. Notice that those are the equivalent answers. This allows us to see something that is actually a general trend that we won't prove in this class, but you will be able to prove in graduate level mathematics. This is called Fubini's theorem. It says this thing. Given that your function is continuous on its domain. Meaning it's continuous on this region R. And clearly our region R is defined as before. The Cartesian product of the closed interval AB with the closed interval CD. So let's apply Fubini's theorem. What's this integral? Where our region R is the set of xy, an element in R2, such that x ranges from 2, 0, and y ranges from 2 to 1. Okay. So this then becomes the integral from, let's say, 1 to 2, integral from 0 to 2 of x minus 3y squared dx and dy. Okay? But alternatively, we can then switch the order of integration and say this is the same thing as the integral from 0 to 2, integral from 1 to 2 of x minus 3y squared dy dx. So whichever one makes your integration easier is the one you should pick. Because mathematicians are lazy, and mathematics is time consuming. Okay? But that's why we love it. So then notice that the integral distributes to both of these terms, meaning when we integrate with respect to y, I get xy minus 3y cubed all over 3. All of this evaluated at y is equal to 2, y is equal to 1, dx. This is the same thing as the integral from 0 to 2 of this big thing, dx, where I'm now going to replace the y's in this following evaluation. So this is going to be x times 2 minus the 3's cancel, minus 2 cubed, minus the quantity x times 1 minus 1 cubed. So that ends up equaling the integral from 0 to 2 something something dx. That becomes a 2 minus 8, 2x minus 8. That becomes a negative x, and that becomes a positive 1 when I distribute the negative. So then these end up equaling, this is supposed to work up, integral of 0 to 2 of x minus 7 dx. And then we integrate that to get that this is equal to x squared over 2 minus 7x evaluated at 0 to 2. Which ends up equaling 2 squared all over 2 minus 7 times 2 minus 0 over 2 squared minus 7 times 0. This whole thing is 0. Don't even care about that now. 2 squared over 2 is just a 2 minus a 14. Becomes a negative 12. Fubini's theorem says it doesn't have the order which you integrate. Okay, so what about this integral? Well, I got to work with the stubs. Let's say our region R is defined as where x is an element of this piece, y is an element of that piece. As usual, x comes first. And so this is equivalent to the integral from 1 to 2, integral from 0 to pi of y sine of x, y, dx, and dy, right? Notice that this is a better alternative to integrating this because all we have to do is use substitution. If you flip the order and dy was being integrated first, if y was the variable, you'd have to use integration by parts. That's more of a tedious and laborious calculation, right? Integration by parts. So let's just use u substitution. Set u equal to xy. Du dx is then equal to y. Then du is equal to y dx. That implies that dx is equal to du divided by y. So then this can be replaced by integral 0 to pi, integral 1 to 2, y sine of u times du over y. dy. Notice that these y's now beautifully cancel. It's a good thing we chose to do u substitution. All right, now it's just, this is the integral sine of u, du. What's the integral sine of u? Oh, I'm not sure. Maybe we'll see. This is how I think about it. I think if du of cosine of u, derivative of cosine is negative sine of u, then I put that here. Right? Then I integrate both sides using the fundamental theorem of calculus. This means the negative cosine of u, the integral sine of u, u. Aha, we verified you're correct. But that's why it's right. And so this becomes the integral from 0 to pi of negative cosine of u, evaluated from 1 to 2 dy. And so we substitute a variable. So this becomes negative cosine of xy, evaluated from x equals 2, y equals 1, or x equals 1, dy. Right? X equals that. So this becomes integral from 0 to pi of negative, and now we can factor out a negative. So this becomes cosine of 2y minus cosine of just a y dy. Bringing the calculation over here, this becomes an integral from 0 to pi. That becomes negative cosine of 2y plus cosine of y. dy. The integral is a linear operator, meaning that it can distribute to both of these. Notice that we can do u substitution here again. And then that means du is equal to 2 dy, which means dy is equal to du over 2. So then this becomes an integral of negative cosine of u times du over 2. So this becomes negative. What's the integral of cosine? Yes. The integral of cosine is sine. So this ends up becoming negative 1/2 sine of 2y evaluated at 0 and pi. So over here we get negative 1/2 sine of 2 pi minus sine of 0. Both of these are 0. So that negative 1/2 times that is 0. And that was this integral. This whole thing is 0. Let's find that last integral to see what this integral equals. Only what that last piece contributes will be what the integral's value is, because that other piece is 0. So what's the integral of a cosine? Yes. So this becomes sine of y evaluated at 0 to pi. This becomes sine of pi minus sine of 0. This is 0. So the total integral is 0 plus 0, which is 0. One last thing. There's one more theorem. Let's say we want to compute such an integral, a product of two functions and the variables x and y. Notice that we can decompose this integral as this. Because as I told you, the differential cross-sectional area element is the same thing as the product of two differentials, because it gives you a little patch of area. And here's our R. If we define R to be the quintessential R that we've been defining it as, some type of closed interval, then this then could be right. So do you remember the limit law that said that the limits as x approaches a of f of x times g of x is this? That the limit of a product is a product of the limits. Do you remember this limit law?
Yeah.
Well, the integral is a fancy limit. It's a limit of a sum, and limits travel across sums as well. The limit of a sum is the sum of the limits. So, because of that fact, this can break down to the integral from a to b of g of x dx times the integral of c to d of h of y dy. That's the theorem. I mean, you know, duh. Because when you do integration dx, it will think any function in y is a constant. So duh, right? This is a pretty duh kind of thing. Because before what we were doing is like integral, we're doing this, right? And then we said, okay, well, then it ignores the h of y. So it becomes integral of c to d h of y. It ignores it, and it's just integrating that g of x from a to b dx. But then we had that dy out here. You know, the dy could come over here. Because we exist in a commutative field, meaning, what's 3 times 4? Okay, what's 4 times 3? Yeah, so the order in which we multiply doesn't matter. Same thing, the order in which the dx is in this product doesn't matter, so we can send it over there. So then you can apply that theorem to solve this kind of an integral. I'm just going to write the integral, and I'm going to let you flee off to your other class. Right? Where I can give you, you know, limits, let's say 0 to pi over 2, 0 to pi, whatever. You can calculate that integral now. You could just say, oh, that's just the integral of 0 to pi cosine of x dx times the integral of 0 to pi over 2 sine of y dy.